Good. So this is what we do. The vowel area or articulation measure is a complex measure in usually squared hertz or square mel or square barks. We don't want to deal with all the phonetic stuff. Sorry, Chris, who's also a phonetician. But we want to deal with measures and scales that we all understand. So what we do is we standardize the vowel area. We subtract the mean and we divide by the standard deviation, right? With Z scoring it. I'm sure you're all familiar with this. Why would we do that? It's because we know this scale. All of you know this scale. It has a limited range. If the data is roughly normal distributed, you should expect that the data will range now between -3 and +3, right? 3 standard deviations from the mean of 0. It makes it easier to compare with other studies that might be used different kinds of scales. We can all convert them to these scale. Once we start building the models, the beta coefficient is going to be on the same scale as the Cohen's d. Right? The difference between the two registers is going to be on the same scale as Cohen's d, which again grants us a lot of basic knowledge that as scientists we have in terms of effect sizes, which makes it easier to apply to our model the kind of knowledge and intuition that we have about effect sizes in our domain. So this is the scale we're going to work at. So as I said, we're modeling articulation or vowel area as a normal distribution. And you all know normal distribution is defined by 2 parameters, right? The mean and the standard deviation, or if we want to be Greek and fancy, the mu and the sigma. I'm going to use these 2 interchangeably. And that's what we want to estimate, right? We want to know simply at this stage, what's the mean of the vowel space area and what's the standard deviation of the vowel space area, right? These corresponds to defining a formula. I'm calling it here articulation F1 because it's the first that we're going to build. And we attribute to this formula using the BRMS function BF, Bayesian formula, the simple syntax of articulation tilde 1, which means that articulation is distributed as a normal distribution with 2 parameters, a mu and a sigma. And we want to estimate the mu and the sigma. That's it. You should be familiar with this from LME4 or whatever other software you use. Now, as you know, we need to build priors in our Bayesian model. We don't just calculate the mean as such, but we need to specify what we know. Otherwise, it's not Bayesian. We don't want to be clever. We don't want to have to think through what the priors we need to define are, because now it's easy, but it will get harder and harder as we get forward in the complex model. So what we say, there's a very nice handy function called getPrior, where we say, okay, this is the formula articulation F1. This is the data we're going to feed it, D. And the family that is the likelihood function is a Gaussian function. And it spits out which are the priors that we need to set. And it tells us, you'll see it in the exercise, but basically that there's 2 priors we need to set. One is the intercept and the other is the sigma. The intercept is the mu, the sigma is the standard deviation, right? And just to make these very explicit, what is the intercept of mu, right? It's the mean expected value of articulation. That is, if we didn't know anything else, what would we expect the vowel space area to be when we sample a new participant? While sigma is the average expected error when predicting data points from the mean. That is, if we just use the mean to predict the vowel space area, the next measurement from a new participant, how big should we expect to make an error? the same thing as saying the standard deviation. It's just a different way, right? Mathematically, it's the same. Mean expected value, mean expected error. So we need to set priors, and that's where we get to the flesh of the thing, right? We want to set a prior for the mean or mu or the intercept. And we need to think carefully about what we know. And here, having rescaled the data makes it very easy, right? The data has been scaled, it's centered at 1, and it's divided by its standard deviation, which means that its standard deviation is now 1. Right? So this is how we could put the prior, right? We set the mean at 0 and the standard deviation at 1. Here is the syntax. We just say the prior for class intercept, for the parameter intercept, is a normal distribution with a mean of 0 and a standard deviation of 1. And this is how it looks like. It's simply simulating a normal distribution, randomly sampling from a normal distribution with a mean of 0 and a standard deviation of 1. And you can clearly see that most of the probability mass is between -2 and 2. Usually at this point, I see puzzled faces amongst my students, simply because we have a mean that has a prior, which has a mean and a standard deviation. Right? Is this a problem for you? Right. So the basic idea is that in Bayesian inference, we embrace the fact that we are uncertain. Right? We don't know things for sure. So when we say that we need to set prior expectation, we need to define what we know about the mean, we do that using a distribution. And the Gaussian distribution is reasonable one here. So basically a mean can have a prior with a mean and a standard deviation. And the standard deviation, as we see in the next slide, might have a prior that has a mean and a standard deviation. How do we set the prior for sigma, right? Again, rescaling the data made things very easy for us. Right? This data is scaled, which means that one standard deviation, one average error in predicting the data points from the mean is 1. So we expect our model to do approximately like the mean in predicting our data, since that is our model. Like the current model is just the mean, basically. So we start by writing prior, normal distribution, mean of 1. That's the average expected error. We don't know the standard deviation yet, and we specify that that's the prior for sigma. So the next step is sometimes tricky. Now I've run it for so many times that it's not tricky for me anymore, but I realized that it might be for other people. But what should we expect our uncertainty in the size of the average error to be? And I don't know, anybody wants to have a go? It's not intuitive, so it's absolutely okay if you don't have an intuition so far.
Would we potentially want it to be like infinite overall possible, like from negative infinity to positive infinity, so it doesn't have any information about what we expect the width of the error to be?
Okay, that's an interesting answer. So the idea is we don't want to impact our model, so we want it to go all the way. What I would argue is that we know more than that. Right? That would be a situation when we don't know anything. But for instance, what I would argue is that our data goes roughly on a range of 6 standard deviations, right? Because we scaled it. So an error that is way above 6 standard deviation is kind of unlikely. Wouldn't you agree? Right. So we want to constrain the space in which the algorithm looks for errors to errors that are actually plausible. Right. If we might potentially have like an error of -1,000, right? If we predict something that's very, very high. but then we really messed up, right? And that will show up other places in the model as well. So my suggestion is that what we want is that we want to be optimistic and say that in principle, but very unlikely, the error could go all the way down to 0. Like 1 is sort of the error that we expect, given that we scale the data that way and we're only using the mean as a model. But a realistic expectation is that it could go all the way down to 0, because that prepares us to other models that we're going to do after. So what we can do is we can have a standard deviation of 0.5, right, which means that 2 standard deviations from the mean will bring us to 0. And we can represent it, right? And it shows that the error can go all the way up to 3, but and all the way down to 0. Again, we might feel uncertain, right? Especially at the first stages of modeling Bayes, but generally uncertainty is a skill to cultivate. And we'll see that we're going to check these priors, right? We're not just accept them as they are. But this is a principled way of setting them up. Okay, so we just use that representation to fill in the different values. And the next question is, okay, we set them up. Are we doing anything meaningful? Right. So let's check. This is our prior. I call it articulation P1, right? And I just create a list with the 2 separate priors. And then we simulate the mean expected value. Our norm, you probably know it, is just sampling from a normal distribution, 10,000 samples with a mean of 0 and the standard deviation of 1. This is how it looks like. And then what we do is we add the sigma, right? We say that the mean of this normal distribution is a normal distribution centered at 0 with a standard deviation of 1. And the standard deviation is a normal distribution with a mean of 1 and a standard deviation of 0.5. And this is how it looks like, right? So basically, what we're saying is that the blue distribution is the range of expected outcomes. But we expect our outcome, our measures of our space, to be within that range, which is between -6 and 6. Which, given that we scale the data, it makes sense, right? It's in the right order of magnitude. If the plot came up that it went from -1,000 to 1,000, right, we would start worrying, because that's in a completely different region of magnitude. And again, this is not p-hacking, prior hacking. It's simply telling the model what we know about the measurement, right? It's not even about the measures. It's just about the measurement scale that we're using. And as scientists, we know a lot about that. And a lazier and actually, I think, more effective way of doing prior predictive checks, of looking at how the outcome looks like given the priors that we're setting, is implemented in BRMS in the package that we're going to use. So here I'm defining a model, articulation model 1, prior. I give it, well, the function is called BRM, Bayesian regression model. There's a formula, articulation F1. There's the data that we have, deep. There's the likelihood function, that's the Gaussian. And there's the prior, articulation P1. And then we say sample only from the prior. Don't look at the data. Once we've done that and we run that, there is a nice function that's called predictive check, PP check, where we give it the model, we say to draw from the model 100 times, and we get the plot on the right. each of the blue lines is a sampled outcome from the model, and the black line is the actual data. What does it mean to sample 100 times from the model? Right. Remember, even from your frequentist statistics days, each coefficient, each parameter that you have has a mean and a standard error. It means that it's a distribution. We sample from those distributions 100 different values so that we can see the full uncertainty of our predictions. And again, overlaying the black line is not necessary. Sometimes it might feel like cheating, but it helps establishing the scale of the outcomes. Yes, Micah?
I just have a small question. So,
Yeah.
so I understand that you have a prior on the mean and a prior on the sigma.
Yes.
And then this is drawing randomly from that. So is it like on each draw, it's taking a random mean and a random sigma and then generating a sample distribution and then doing that 100 times?
Yes. So the basic idea is as we sample in a Bayesian inference, right, we're moving through the possible space of parameter values, right? So at each movement in these, it's a Hamiltonian Monte Carlo, it's a simulation of a physical particle, but whatever, you know, if you want to, you can think of as the model is trying to optimize, it moves through this parameter space. And so at each step, it finds two values, one for the sigma and one for the mean. When we do PP check, right, we take 100 of these couples because they might be correlated, right? So we don't sample independently, we sample in the joint parameter space. If you want to think it in the traditional framework, yes, what you would do is you have a distribution of mean, a distribution of sigma, and you can randomly sample from the mean and randomly sample from the sigma. Then you have, I don't know, in this case, it's 48 data points. So you, from the new distribution that has the sampled mean and the sampled sigma, you sample 48 values.
Okay, I think that's clear. Like looking at the small line, there's one that's really peaked and really tiny. So that must have been one where the parameters were, where the mean was close to the empirical and the sigma was really small in that sample.
Yes, exactly.
Okay.
And that's since we gave a prior for the mean that's centered at 0, right? That is the most frequently sampled one. Yes. Good. So now we're ready to fit them up, right? We checked our priors. They sort of make sense. We're in the right region. It's not the last checks that we're going to do, but we know that we're not asking the model to search for a mean and a sigma in crazy places. And the only thing that we do compared to the previous code is simply we say that sample prior should not be only, but it should be true. So it should sample the prior, but not just the prior. And then what we do is we can do a posterior predictive check, right? After the model has been fitted, we can run 100 simulation from the model that has seen the data to see just whether the distribution of the outcomes as predicted by the model makes sense, which, if you want, is not too different from the residual checks that you do in more traditional frameworks. Right, so it's the same code as before. We just give it the new model, articulation model 1. Here is what we got before, right, before seeing the data. And this is what we get after seeing the data. Right, we get that the range of the outcomes is very close to the actual data. We get that the shape of the distribution is very close to the shape of the data, right? So this is showing us that there is no huge bias, right? There is no region of the values that is systematically under-predicted or systematically over-predicted. It's roughly decent. Good. Now, what we want to see is which impact the priors have had on our inference. So we want to do what is called a prior posterior update check. We want to see, after seeing the data, how has our estimate of the mean and the sigma changed compared to the prior? Has the model learned from the data? Were the prior sort of keeping the model from learning? Right. On the left, you see the prior posterior check for the intercept. In blue, you see the prior. And in orange, you see the posterior. Right. What you see is that the posterior has gotten much more confident than the prior. It's much narrower and taller, right? It has learned. It has become more confident after seeing the data. We also see that the prior doesn't seem to strongly impact the posterior in the sense that the posterior is not pushing at one of the boundaries. We'll see bad examples in a bit. When we look at sigma, again, we see roughly the same thing. Right? That the posterior has learned, the model has learned the posterior is more pointed than the prior, and that the posterior is solidly within the prior distribution, meaning that it's not pushing, it's not trying to force the hand of the prior. Some people like numbers. As it learned enough, there are some suggestions in the literature, for instance, by Gelman, that a model has learned from the data only if you have a standard deviation in the posterior that's 1/10 of the standard deviation in the prior. As you'll see in the course of the workshop, I have a much more pragmatic attitude that is, it really depends on the problem at hand and on the assumptions of your analysis. We'll see a case later on where not becoming much more confident is okay, in my opinion. But know that there are quantitative measures if you really feel the need, or if you get this usual annoying reviewer too, right? Okay, so in this case, everything seems in place. Right. How would it look if things were bad? And then we'll move to the exercise and break. So for instance, if we put a sigma that had, I don't know, was centered, I think I put it at 30. Right. This is what we might get. The simulations from the model go all the way from -500 to 1,000, while the data is solidly at 0. Right. So basically what this is telling us is that from the priors only, we expect outcomes in a really unrealistic region. I think my favorite example that I learned from Dan Simpson is that there was a study on pollution in which a pretty probable outcome from the priors only required that pollution had basically form a neutron star on Earth, which physically is not, well, maybe physically it would be possible, but it's quite unlikely. So they had to rethink the prior. But what about the posterior check? Let's look at this. Right. Has anybody an idea why I'm saying that this is a bad predictive check? The model has seen the data and has gone quite close to the data. It's roughly in the right order of magnitude of outcomes. What's wrong here? Look at the shape of the real data compared to the shape of the simulations. Let me see the chat. Yes. Well, so let me give you a hint. Imagine that these are reaction times. Do you see anything wrong with the predictions?
It goes below 0?
Exactly. And there is a long tail on the right, which the model is not capturing. So the model is making 2 errors. It's going below 0, and it's assuming that there are no slow responses, which is unrealistic given what we know, right? Of course, we haven't discussed which task this is. I've only simulated the data. But we know that in most tasks, including reaction times, we expect long tails. And we expect nothing below 200 milliseconds. Right. So what's wrong here? Right? Do you have any idea of what went wrong?
Maybe too much weight was given to some of the unlikely samples in the unlikely space, and that it ended up shifting it outside of a reasonable area?
Not exactly. So this is where I was pushing you. So that's a really great answer. So far we've seen problems due to the priors, but the inference is prior plus likelihood, because the priors are going to have a hard time changing the shape of the outcomes, because the shape is determined by the likelihood function. So here we are using a Gaussian, a normal distribution, which doesn't know that there are hard boundaries and that there are asymmetries. And what we could have used, for instance, is a log normal, because a log normal doesn't go below 0 and has long tails by default. Right? If we had a task where we actually have some slow processing time because it's a bit hard, we might even go for what it's called a shifted log normal, meaning that it expects things not to start at 0, but to start at a higher number of milliseconds. Good. What about okay, are there questions here? So this is just, it's giving you tools to visualize what you're doing with your model. Right? This is what you're putting in. Yes, Nia? Or, oh, sorry. Yeah. Okay, but what about the prior posterior updates? Yes. So here we have an example where the posterior hasn't learned a lot from the data, right? It's basically just as confident as the prior, and it has had a hard time moving away from the prior, right? It's pushing at the right boundary. So the blue is the prior, the red is the posterior. So what this might mean is that the prior was too confident and we weren't able to learn given the data that we have. Let's say if we had a small sample size, it's hard for the model to learn, especially when we have a confident prior. But I also put a question mark, right? Because it's not necessarily bad. It really depends on what we're trying to do. Let's say that we have a solid result, right? And we have meta-analytic result and that we believe in, and we do a new study just to replicate. Right? If we want to move the average estimates in an updated meta-analysis, right, we don't want to have this new one study to move the estimate too much, right? Because we believe that the meta-analysis was relying on solid studies that were well-designed, well-powered, and so on and so forth. So we want to keep a certain weight onto the meta-analysis and only allow the new study to move the estimate a bit. And if we see that it moves that way, maybe we should go and collect more data and give more strength to the inference, more data to learn from to the model, but not simply making our prior less confident. On the other hand, if this was our initial prior and we are very uncertain about that, right? We don't have many strong motivations for it, then seeing that the model is not able to learn from the data should make us rethink the prior. Does that make sense? So whether these are bad or a good example, it depends on the structure of the problem. I know this might be frustrating, at least it is for my undergrads, but it's the power of Bayes that it forces you to actually think through your analysis and scientific process. Here is another, right? Here, the data is really strong, right? The posterior has learned a lot, is much more confident than the prior. But we don't know whether it would be much different if we had a more uncertain prior, because it really went out to the tails of the Gaussian distribution of the prior, and it cannot move anymore. Right? Probably if we broaden our prior, we would get a very different estimate. This is generally a bad example, unless we're using it to say this, right? Look, the previous study really doesn't capture what we see in the current study. Look at this plot. It's really pushing it away, even when we combine the information from both. That's also legitimate use. Good, so take home for now, and then maybe we can afford a quick break before the exercise, right, Chris? Yeah. But the take home is we model things one step at a time. Doing this Gaussian modeling of the articulation of the vowel space might seem silly, but it's already telling us something about our measurements and how to set up the model. You always have information that you can use to set up the prior. It's not arbitrary or subjective. There is information about your scientific problem or the measurement scales that you can use. Obsessively check what you're telling the model. And don't be afraid to change and adjust your model. It's not p-hacking. It's trying to describe the data properly. We're not even looking at effects now, right? We're just trying to understand the data.